So I wanted to look a little more closely at the nerve cell and at the myelin sheath and the Schwann cells before we move on to the central nervous system. So notice here we have a typical myelinated nerve cell. Again, notice some familiar structures here, which we've already talked about. Notice as this axon is extending out, we're going to have, and let's look at the cross section here. So here we have the axon. Notice we have a myelin sheath that's surrounding the axon. That myelin sheath is specialized glial cells called oligodendrocytes. And these are those specialized glial cells which will wrap around and insulate and protect that axon. Now, if you're out on the peripheral nervous system, we have this extra layer produced by the Schwann cells. And here's the nuclei of the Schwann cell. And notice there's a region in the wrapping here, and that's the neurolemma. I want you to get that. Just to keep it organized, we have the specialized cells, the oligodendrocytes, which are producing this myelin sheath here. But we have the neurolemma, which is part of the Schwann cell. So if you're at the peripheral nervous system and you're extending out, this cell body here is extending out its axon to, let's say, skeletal muscle. If there's an injury, which can happen all the time, so a deep laceration, deep cut, and what would happen if that's cut? If the axon is cut, we would separate if this axon is cut and you're in the peripheral nervous system with those Schwann cells, again, the central nervous system would only have any sort of myelinated nerve fibers there, would only have these oligodendrocytes, this region here. But if you're in the peripheral nervous system with this neurolemma here, get rid of that, this neurolemma will provide a passageway for the axon here to regenerate and find its way back to the muscle in which it was innervating. So in other words, this is cut. This can grow back now with the help of the neurolemma and grow back and then re-innervate. There's my little synapse. And then re-innervate, let's say, a region of skeletal muscle here that's in the arm, let's say. So we've already talked about the neuromuscular junction. And at that region where the nerve and muscle meet, you're going to have that synapse. That synapse is going to release a neurotransmitter that's going to be acetylcholine. Acetylcholine is then going to diffuse across that synaptic cleft. It's then going to bind with specific receptors. Now, since we've talked about action potentials, when that happens, we're going to get an influx of sodium ions. We know that resting potential is then going to go up towards threshold potential from -70 towards, let's say, for example, -55. Once we hit -55, we're going to get that action potential, and there's going to be a wave of depolarization over the muscle and then deep into the muscle, after which there's going to be a series of biochemical events which are going to result in muscular contraction, where the actin and myosin will slide by one another. So that muscle will in fact shorten then, and then you can run, jump, and lift weights, do whatever. So what we're going to do now, though, is talk about the synapse within the central nervous system. Again, acetylcholine is going to be important, but now we've got a vast array of different neurotransmitters. Some are going to stimulate the nerve, some are going to inhibit the nerve. What are some of these other neurotransmitters? You're going to hear names like serotonin. You're going to hear names like GABA, gamma aminobutyric acid. You're going to hear names like glutamate, several others as well. Dopamine's a famous one as well. So anyway, we'll get back to those in a little bit. Right now, let's take a look at what's going to happen at the synapse here. So notice we can get a close look here, but then look at all the other synapses here as well. So let's take a close look at synaptic transmission here. Let's do it. Here's our synaptic vesicle. May have acetylcholine or any number of different neurotransmitters that would be important. There's the synaptic cleft. This would be a dendrite possibly, or the cell body of a nerve cell.
Action potentials arriving at the presynaptic terminal cause voltage-gated calcium ion channels to open. Calcium ions diffuse into the cell and cause synaptic vesicles to release acetylcholine, a neurotransmitter molecule. Neurotransmitter molecules, acetylcholine, diffuse from the presynaptic terminal across the synaptic cleft and bind to their receptor sites on the ligand-gated sodium channels. This causes the ligand-gated sodium ion channels to open, and sodium diffuses into the cell, making the membrane potential more positive. If the membrane potential reaches threshold level, an action potential will be produced.
So notice a couple important things here. First of all, that acetylcholine is actually going to have an important role in opening up that voltage channel for the sodium. So notice here and here, these are ligand-gated channels. A ligand is simply, or ligand, is simply a chemical messenger which is going to attach to the protein channel here, and it attaches with specificity. So the shape is going to be important. Once you get that ligand-gated channel opened, then notice we can get the influx of these positively charged sodium ions and then stimulate the nerve to threshold. I want you to get, let me recap here, let's make sure we get, let's make sure we get acetylcholine and its actions in both the central nervous system and the peripheral nervous system. Let's look at norepinephrine. I want you to get this as well. So in the central nervous system, a sense of feeling good. Low levels may lead to depression. Dopamine. Get this one as well. I'll give you a moment or two to write those down. Make sure you indicate central nervous system or peripheral nervous system. Serotonin. Serotonin. Central nervous system, primarily inhibitory, leads to sleepiness Action is blocked by LSD, enhanced by selective serotonin reuptake inhibitor drugs. Get that word for word. Now, we've talked about amino acids as being components of the building blocks of protein. So amino acids have been adapted by the brain, and they can serve as neurotransmitters. 20 different amino acids. A few of these can serve as neurotransmitters. Here's GABA, and here's glutamic acid. They're both central nervous system. One is inhibitory and one is excitatory. So one is going to the excitatory neurotransmitter is going to increase permeability to sodium. Sodium again comes in. Resting potential at -70 is going to go up as those positives go in. Then we're going to reach threshold and fire away. Notice inhibitory. Going to be a little bit different. Something inhibitory is going to lower the resting potential, making it further and further away from threshold stimuli. I want you to get substance P. So that's excitatory, and that's pain perception. Substance P. Excitatory and pain perception. Endorphins and enkephalins. I want you to get these. These are inhibitory in general. They can reduce pain by inhibiting substance P. So these endorphins and enkephalins reduce pain. So I want you to have all of these in your notes, and I want you to look over them. Be prepared. You are going to be responsible for this information in a real sort of way, and I mean a real sort of way. Very important also. All right, so that's a look at neurotransmitters.